Yeah, now you can start.
Okay. All right. Hello everyone. Good morning, good afternoon, good evening, good night. Hello world. Hello everyone. Welcome to the 19th session of the ISRM Young Members Seminar Series. First, thank you for being here. I would like to introduce the organizing members for this event. My name is Kisop Kim. I'm an assistant professor at petroleum engineering at Texas A&M University. And Cecilia and others, would you like to shortly introduce yourselves?
Well, I'm Cecilia Laskowski. I'm from the Universidad Nacional de la Patagonia San Juan Bosco, Argentina.
And Kimi?
Yes, I'm Kimi Suzuki. I'm an assistant professor of the University of Chile and also moderator of this session.
Yeah, so yeah, and we are the part of the ISRM Young Members Group, and we're happy to chair this 19th seminar. So it's a great pleasure for us to be here today, and then we would like to thank you for attending this 19th session. And before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Esteban Hormazabal, ISRM Vice President for Latin America and Chair of the ISRM Young Members Committee. And we also would like to thank to all young member representatives of national groups that have joined this initiative. And finally, we would like to thank Dr. Dr. Lucas and Hyunbin and Edison and Isaac for agreeing to present their great work in this session. So before our speakers begin, we would like to, oh, I'm not sharing my screen, sorry. You can see my screen, right?
Yes, we can see.
Okay. Okay, so before our speakers begin, we would like to take a moment to present the key information about the seminar series. So this project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, and to strengthen relations between different countries. We would like to invite a variety of young members to participate in this seminar series. The criteria for the speakers are as follows. Be an ISRM member and have a maximum age of 35 years or 40 years if a PhD degree was obtained in the previous 5 years, and have worked in rock mechanics and rock engineering for a period no longer than 10 years. Okay, and then and how you can apply. So speaker nominations for this event can be made by the nominees national group or by some other person or organization acquainted with the nominee's work. Self-nominations are also accepted, and nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. On the screen, you can see the our contact email, and feel free to reach out. And this webinar will be held every month, and we invite you all to keep in touch. So with that, we would like to start the first seminar for the day. We have 4 seminar speakers for this session. And each presentation will last for 20 minutes and will be followed by 10 minutes of Q&A. And for the smooth running of the seminar, please turn off your camera and microphone during the presentation. And if you have any questions, you can use the chat and also use the raise hand feature. So let's get started. So I would like to first introduce the first speaker. The first speaker is Dr. Luca Bellini Machado, who is a Brazilian civil engineer and PhD in geotechnical engineering from the Polytechnic School of the University of São Paulo, under the supervision of Professor Marco Massaofutai. His research focuses on the application of Industry 4.0 concepts to underground infrastructure, particularly the development of digital twins for tunnel inspection, degradation assessment, predictive performance modeling, rock mass characterization, and discrete fracture network modeling for permeability analysis in complex rock tunnels. He completed international research internships at the National Laboratory for Civil Engineering, Portugal, with the Urban and Transportation Geotechnics Unit under the supervision of Joana Maria Carreto, and at Polytechnic Montreal, Canada, in the Department of Civil, Geological, and Mining Engineering, under the supervision of Professor Pedro Pazo Casiari. He has authored multiple peer-reviewed articles in leading journals such as Tunneling and Underground Space Technology and Journal of Infrastructure Systems, as well as papers presented at international conferences. And today he will be presenting a talk entitled Digital Twin Construction for Life Cycle Analysis of Tunnels. So with that, Dr. Bellini Machado, the floor is yours. So I will stop sharing, and then, yeah, Lucas, you can start sharing your screen.
Thank you so much for the presentation. Let's see. Okay, you can see my screen. Can you see?
Yes.
Yep, you can see. Yep.
Okay, it's good. Let's start. Okay, I'm glad for the opportunity to share my research, named Digital Twin Construction for Life Cycle Analysis of Tunnels. This is an overview of my research, where you have three different phases: the definition, the core development, and the application. The definition, it's more about we want to define what is a digital twin, the concept, what we need, and the difference between the digital twin and a normal and our common application of simulation. In the next phase, we have the core development, where you have two different case of studies in tunnels. This phase it's about to build the environment, a digital environment, understand the digital twin methodology demands, and create and build this digital twin environment for tunnels and for great infrastructures. And the last phase, it's here I focus in this phase because it's about to apply in test and application in unlined tunnel in Brazil. It's a rock unlined tunnel. When we use these tools to assessment the rock mass permeability and infiltration using the susceptibility, calculating the susceptibility zones and water inflow. Here we have the introduction of the definition. You can see in last year's the number of papers about this topic in civil infrastructures, the digital twins. It's a hype in this last years, and it's more common in different areas of industry, not too much in the civil infrastructures. This is a new apply of this type of methodology. We can connect this with the life cycle phase of tunnels, of infrastructures as well. We have design and operation maintenance. We can do this for classification or digital twin. We have uses too, where you have different complexity levels. We have just for digitalize something, or we can go to predict something for tunnels, infrastructures, or rock mechanics. It's the predictive. We need to know more about the rock mass. That's why we started to use district factory networks to understand the seepage path inside the rock mass. That's why we need to know more about the rock mass in our work here to predict something, to orchestrate something and understand the behavior of the structure with the time. Here you have the associated technologies. We for defining the digital twin, we did some research questions for understand this technology. Well, the associated technology, the first one, modeling, sensors, numerical analysis, everything together. It's the mainly technologies for create a digital twin. The intended uses, we have the tunnel the tunnel have the application infrastructures like tunnels, we have the most complex levels than other infrastructures. We have the applications in simulation, orchestrating, and extracting. It's the high complexity levels. The frequency of application compared to other infrastructures, we have application in grids, tunnels. It's a little bit more in grids than tunnels, but we have 25%. The life cycle phase of application, it's important because we want to know what specific life cycle phase the digital twin methodology can be more applied, and you have the operation maintenance. Makes sense because the definition of digital twin, you have the physical asset and the virtual asset, and connect this information. It's everything makes sense with the monitoring approach or something like this for optimization and maintenance, but can be applied for other phase like design, special case. Here we start to define your prediction. We have different standards, and we use this to create our specific standard, our specific methodology framework to predict the behavior of tunnel with the time, and using the inspection data of tunnels. We use different reference source for this and create our own methodology, our own framework to apply. Here we have this inspection serviceability assessment of methodology. It's the methodology. We have the tunnel. Here's the first one, the tunnel one. We have the shotcrete tunnel lined in Brazil, the north of Brazil. We did a defect location in a grid, where you have the right wall, roof, and left wall. We have a lot of these blue marks are the water inflow inside the structure. You can see the water inflow is the most common defect that we have in the tunnel, and we classify this. We assign tunnel serviceability index value just to quantify. Use our curves to calculate to try to predict the behavior of tunnel with the time, and use some inverse exponential equations. It's normal for tunnels to try to predict the curve behavior. We start with the digital twin. It's about to modeling and digitalize something. When we start to do this in Rhino, we did a model where we just use this. We named this model as the inspection digital twin prototype, and we create a model with these specific zones with more or less defects and classificate. We insert metadata inside these objects and use the state evaluation to quantify the performance and the serviceability of this specific tunnel. To upgrade this model to increase the level of details and the physical and virtual connection and automation of this process, we use field data acquisition, data adaptability, and advanced modeling techniques to do this. We use the terrestrial laser scan to scan the second tunnel. This is the second one, the coastal tunnel. And we did use the data adaptability, where we have it's the same thing about the advanced modeling techniques. We use parametric modeling using Grasshopper. It's a visual graphical language to do this. And with this, we can have some lacks of information about point cloud or something like this. And the mesh can adapt with your data and the flexibility about this. Here you have the parametric modeling, how this works. You have boxes with operators, and you can put this in a row or in parallel, and you can just update some parameter inside some specific step, and it updates automatically your model. This is important to create some automation in the model creation, and the focus is not in the result, it's in the process of the construction of the model. Here you have the automation in the data information located in the tunnel. We have some CSV. You can use this CSV data from different sources. You can do some non-destructive tests. You can do some sensors data. And with this specific script, you can just locate this automatically in tunnel. And you have some informations like key values format, where you can put these informations inside the structure with the script, the developed script. Here is the final result of this part of the research. When you have how is the result previously with 2D, we just have a grid 2D, and now we have the 3D, we have each area located, the area is created with the format of the point cloud, you have the geometry concept, now data of the geometry, you can prove the reliability of your data set, the location of this, and you have the informations, photos. This is our results about the states for each tunnel position. And again, in this tunnel, we have the leakage problems. This is why I want to, we need to search more about the rock mass. I think in this step of this work, we want to know more, not more about just the excavation and surface, but we want to know more about the excavation, the rock mass, the fractures, the discrete fractures network, to understand the seepage, because for predicting the life cycle, to understand the seepage, to understand the water leakage inside the tunnel, we want to know more about the behavior. We want to understand this process, to understand the fractures inside the rock mass. Here it's the tunnel permeability assessment introduction. We started water ingress tunnels is strongly influenced by fracture network geometry and surrounding rock mass. Understand disconnection and understand the seepage is crucial for safe design and construction and long-term performance. The connectivity and the flow, we use the discrete fracture network modeling. We need to have reliable data from the structure to do this, because if you don't have it, the stochastic process, you not create a reliable model. And we use the LiDAR to do this, and use the 3D, the software 3D from Tasca to create this and apply the optimization process. We have the LiDAR mapping for DFN inputs, and the LiDAR scanning was used to capture details of the surface. Here's the first step, using the LiDAR to create a based DFN as information. Employs automatic discontinuity analysis to determine the probabilistic density distribution. We use the mapping window scanning in tunnel to determine this distribution for size and for orientation of the fractures in the aligned tunnel. This is application now, it's an aligned tunnel. You can see every factory, you can see everything inside the tunnel. We use the LiDAR to scanning and take this data. And using this to understand the joint set families, the different joint set families, and calculate the P32. The P32 is the area of fractures divided by the volume analyzed volume, but that's impossible to measure this in field. And we use the P20, it's the number of fractures in a specific sample window, and use simulations to determine the P32 as stop criteria. For this, we did the representative elementary volume and the mean stability, 10% of coefficient of variance, for increase the reliability of the P32. And here we have the factory network, how this works, how this is this model, the distribution of factories, it's the disks of factories, and we have 3 different families here. Here it's the fish script algorithm implemented in this phase of work. We have a specific position in tunnel. We extract the information about the joint sets. We have the size, the orientation. With this, the DFN is generated. After that, we apply a specific permeability DFN optimization that we developed using deleting the non-connected fractures and isolated clusters that don't contribute with the permeability and seepage path inside the structure. And after that, we calculate the mean indexes for this. The mean index is what we just choose to calculate the permeability with the permeability tensor by Oda, proposed by Oda, and use the rotation metrics to calculate the permeability location in the tunnel walls. We just, after this calculation, we have the results, and the looping goes to the next position of tunnels and do the same looping again. And with this looping, we can just calculate in the index for each position of tunnel, creating DFNs and models, different models, apply the optimization, and calculating the indexes. Here we have an overview of everything. We have the discontinuity mapping, trace mapping, discontinuity analysis, the Fisher. I don't say this before. We assume this isotopic Fisher distribution and discontinuity analysis. We created the DFN model, the DFN disks. After that, we calculate the permeability tensor, rotate the matrix tensor to calculate the directional permeability analysis, and with this, we know using the rotation matrix in y-axis, and with this, we have the permeability in tunnel walls, calculated permeability in tunnel walls using the information of the fracture, the distribution stereograph fracture information, and compare this with our previous model development using the parametrical modeling, and our group performed geophysical tests in field to compare this with your results to validate our calculation. Here you have the stereogram from geological mapping. We have 3 different families of joint sets. We use the permeability tensor invariant, the first one for the magnitude of permeability, and the second one for the directional anisotropy of the permeability. This is the optimization evaluation. We use the first invariant to calculate the optimized permeability and non-optimized permeability, or the raw. We just have the 2-1 and compare. It's possible to see when the DFN, the fracture network, it's too connected. The optimization does not work. They don't delete or exclude nothing. And it's possible to see in some regions about 100 or 140 in the tunnel position. The optimization does not work because all the connections, all the fractures are connected in this specific position. And you have the optimization efficiency too in the stage 1, the let just fractures non-connected, and the second stage, the letting the non-connected and isolated clusters. How this work? How work it is? This is the number of connectivity clusters. When you have again the connectivity index, we have something to understand why the optimization did not work in some times. And we have the permeability invariance along the tunnel. When you have different combinations of joint sets, we have J1 and J2, J3 or J1. In this specific position, when you have more or less permeability index calculated. We proposed a new anisotropic permeability index, the EP1, the deviatoric permeability vector, because what we found in our research is the second invariant is not too much sensitive for some specific positions, and we found and proposed a new index for understand better that for calculate this anisotropy property inside the tunnel, inside the rock mass. Here it's the connection between the calculated permeability and the parametrical modeling leakage zones found in the LiDAR scan. It's possible to see we have 3 different zones with leakage stands, with water stands, and with this we have the zone 3 with more the great permeability calculation, the great permeability values. And in this specific zone, zone 3, it's possible to see the J2 and the J1 has more contribute more for the seepage and the flow inside the tunnel for our calculation method. Here it's the results about the electrical resistivity tomography. It's the geophysical test. We have the calibration, and the figure B in right, it's the specific zone tree. When you have a layer of soil, and this layer you have a great level of groundwater, and this water enter in the tunnel using the fractures, the distribution of fractures, and this is specific. That's what we want. We want to know more about understand the water flow inside the tunnel. That's what we saw in field. Like the water goes to the tunnel using the family 2 and family 1. The family 3 not too much here. It have some connection with your calculation. Sorry. And here we have the directional permeability calculation, where we can just assume it's some aperture. It's really difficult to measure the aperture in field. We assume this to calculate, and you have the directional permeability, the mean directional vector for each permeability direction. Wet areas calculated using the model, the concept of model, and find the wet areas, the parametrical modeling. And here we have the position. It's possible to see the mean directional vector. It's connected. It's in concordance with the J1 and J2 positions that can be explained by in the zone tree. This be explained by the geophysical results. This is my reference. This is my paper is published, and I'm glad to share my research here, and thank you so much.
Thank you very much, Lucas, for your interesting presentation. Now we have 10 minutes for the question and answer session. Does anyone have any questions? You can raise your hands, or maybe just open your microphone and make the questions if you have any. Or maybe you can just write them on the chat if you are a little bit shy. Okay, I think there are no questions. Thank you, Lucas, once more. It was really interesting hearing about Brazil and hearing about your research. So, well, we will continue with the following presenter. The next presenter is Dr. Hyunbin Kim, who is a postdoctoral scholar in structural engineering at the University of California, San Diego. He received, sorry, I'm not sharing my screen. I should be sharing my screen. Share. Okay, so now, yes, sorry, once more. The next presenter is Dr. Hyunbin Kim, who is a postdoctoral scholar in structural engineering at the University of California, San Diego. He received his PhD in civil and environmental engineering from the University of Illinois Urbana-Champaign in 2025. His research focuses on coupled hydromechanical chemical processes in geomaterials, including capillary phenomena, multiphase flow, pore mechanics, and petrophysical characterization of low permeability rocks for applications such as carbon sequestration, hydrogen storage, and nuclear waste disposal. He has authored multiple journal articles on Caprock integrity and fluid rock interactions, and has received several awards, including Mavis Future Faculty Fellowship at UIUC and Best Oral Presentation Award at CoFRAC 2024. At UC San Diego, he is currently developing experimental and constitutive frameworks to characterize the thermo-hydromechanical behavior of compacted bentonite for nuclear waste disposal applications. Today, he will be presenting a talk entitled Caprock Integrity in Geological Carbon Storage, Effects of Heterogeneity uncoupled processes. Hyunbin, I will be stopping with. Okay. Stop sharing. There you are able to share your screen.
Now, can you see my screen now?
Yes, yes.
Yes. So, yeah, good afternoon or good evening, good night. My name is Hyunbin Kim, and first, thank you for inviting me today. So, I'm currently working as a postdoc scholar at the University of California, San Diego. And today I was going to present about part of my PhD research on the Caprock integrity in geologic carbon storage with a special focus on the effect of heterogeneity and coupled process. Yeah, so this talk is a part of the large portion of the subsurface geoenergy system, which including the underground hydrogen storage, carbon sequestration, geothermal system, or the nuclear waste repository. So the geoenergy system, the major that have in common is that the subsurface geomaterials will subject the multiphysical coupled process, and this multiphysical process will change the pore structure, transport properties, and long-term integrity. And today's talk is more focused on the geologic carbon storage, which has been considered one of promising technology to mitigate the carbon dioxide in the atmosphere. So in this application, we capture the CO2 from the atmosphere or the other large source and then store it in a deep reservoir. So there are a number of the candidate can be considered as the potential injection site, but most of the research and the rear injection sites adopt the deep saline aquifer. And in this geologic formation, the low permeable low permeable layer called Caprock formation will usually be placed on the top of the reservoir, and then this Caprock will serve as the primary seal since the injected CO2 is moved upward after the injection due to the buoyancy pressure. So let's more talk about how the Caprock formation is actually preventing the leakage. So first, the captured CO2 will be compressed as the supercritical condition due to the higher efficiency. After that, we find some like a reservoir which is under certain depths, usually over the 800-meter, to preserve the state as the supercritical condition. So once we inject the supercritical CO2, as mentioned, the injected CO2 is start moving upward because of the density difference between the in situ brine and the injected CO2. At the same time, the injected CO2 is start dissolving into the in situ brine and diffuse on the bottom of the Caprock formation. However, because of the slow rate of this diffusion process, so it's hard to move a meter for several thousands a year. So the main mechanism of the sealing mechanism of the Caprock formation is mainly governed by the capillary properties, because the injected CO2 is a non-wetting fluid compared to the in situ brine. So it means that when you have the Caprock formation has a small pore size, it's easily to prevent the upward migration of the injected CO2. And if the Caprock formation has a large pores because of some heterogeneity, the CO2 readily goes through the Caprock formation and start migrating through the overlying formations. And once the CO2 is start intruding into the formation, the coupled process will govern the sealing mechanism. So in principle, the concept is quite straightforward, but in practice, the long-term storage efficiency strongly depends on whether the Caprock is actually prevent the upward migration over the geologic timescale. So usually in the fields, the shales or the clay stones are adopted as a potential material for the caprock because of their abundance and then the favorable characteristics such as the low porosity, low permeability, or the nanoscale dominant pore size. In this talk, I mainly focus on the several representative material, including the polynos clay, Maquoketa shale, and the clear shale. Those came from the actual or potential injection site. And as you can see here, like within this the title of each material, you can see the very strong like a variation in the mineralogy or the resulting the pore structures. And this variability turns out to like first order controlling the factor for the sealing performance. So at the field scale, we also can more readily see some heterogeneity. So here is the example about the Maquoketa shale that I introduced before. So it's come from the Illinois basin. And then if we extract the core, the continuous core from the potential injection site, we can see some clear inclusion of this limestone into the formation. And then there's one case study also shows that there's some heterogeneity in the Caprock formation actually cannot prevent the leakage of the CO2 throughout the overlaying formation. So this story tells us that the Caprock formation may contain some like sand or the sandstone on the limestone interval, like a lamination or other geological features that create some like a weak zone, local weak zone. And if this the Caprock formation looks suitable on average, and this local heterogeneity may control where the CO2 can actually like enter and then migrate. So this all the story and the multi-stage sealing mechanism of the Caprock formation leads to the main question of this talk, is that how the heterogeneity and coupled process control the Caprock sealing performance. So to study that in a control way, we have adopted the series of the experimental methods using on the heterogeneous Caprock that I introduced before. First, we characterize the material, the pore structure properties of the tested material using a method called such as the mercury intrusion porosimetry, nitrogen absorption, or scanning electron microscopy. We also measure some transport properties such as the permeability or the breakthrough pressure using the cold flooding system. We characterize the coupled process of the tested material under a reservoir condition. However, in this talk, I mainly focus on the transport mechanism on the heterogeneous Caprock material. So I will mainly focus on to introducing the cold flooding system we have been utilized during our research. So in the system, we first core the specimen and then place into the core holder, then apply the lateral confining pressure using the pressure controller. At the same time, we have connected on the upstream and the downstream using a separated syringe pump to control the fluid pressure or the flux into the tight material. Due to the configuration of this device, the total mean stress can be calculated as the follow. And then before any of the measurements to evaluate the sealing potential of the Caprock material, we have to based on the experimental protocol, we have to make it the specimen as a given saturation. And in this case, we have adopted the back pressure saturation to fully saturate the specimen before any of the testing. And because of the nanoporous structure and then the low permeability, it requires several months to fully saturate with even under the high back pressure condition. So after we fully saturate the specimen, now it's time to measure the breakthrough pressure first. So as mentioned, the breakthrough mechanism is related to the capillarity between the CO2, liquid CO2, and then the brine. And then it's also related to the pore structure too. And this capillary mechanism is readily explained by the retention curve, which correlate between the capillary pressure and the fluid saturation. And here is just schematic view of the full range of the wetting and the wetting and drying curve of the retention curve. And then we can simply divide this stage as the four condition based on the direction of the saturation and then the direction of the saturation and then the range of the capillary pressure. However, in this condition, we mainly focus on the breakthrough pressure because there is it represents the best similarity that the CO2 is stored the CO2 in the reservoir is start intruding into the caprock that has been saturated with in situ brine. So to measure the breakthrough pressure, we use the same core flowing system, but now after we saturate the specimen, we replace the upstream fluid as liquid CO2 and adopt the stepwise method in which that the upstream pressure is increased in a stepwise manner. So before the CO2 is start intruding into the rock specimen, we could not see any change of the upstream and the downstream volume change. But once we establish the differential pressure is comparable to the breakthrough pressure, we can see the onset of the upstream and the downstream flow rate, which can be considered as the onset of the breakthrough. So based on this approach, we first do the test with all heterogeneous material in this study. And then we first found that in the same formation as we expected, the clay-rich material has a higher breakthrough pressure compared to the sandy counterpart. And then some of the material has the breakthrough pressure is changes over on the order of the magnitude difference. And then we found the negative correlation between a dominant pore size and then the breakthrough pressure, which also can be readily described by the Young's Laplace equation. But we also saw by comparing with the other reference, we see that some superpositioning is required to fit the breakthrough pressure with the dominant pore size. After that, we expanded this research using a statistical analysis to correlate the breakthrough pressure with other rock properties. And then we found some clear correlation with the clay contents and the dominant pore size with breakthrough pressure. And we couldn't see any correlation with the specific surface area or the weak porosity because the breakthrough mechanism is mainly related to the size of the pore conduit rather than the volume itself. And then after that, what does that mean at the field? So using this measured breakthrough pressure data, we also can estimate whether the different materials are able to support at a given CO2 column height. So in this implication, we adopted the ceiling number, the term ceiling number, which is the ratio of the measured breakthrough pressure, and then calculating the buoyancy pressure at a given CO2 column height. And then this CO2 column height is actually representing the size of the injection site. And then we can see that below the ceiling number 1 is prone to leakage. And then in the case of the pilot scale, we can see that most of the specimen can be still act as the effective seal. But when we increase the scale, some of the parts, especially in a Makwakta shale, we can see that some clay parts will be still serve as the effective seal, but most of the CO2 may be able to leak through the sand-rich part. So this result also shows that along with the multi-scale experiments on the breakthrough, we also need the high resolution mapping and the refined stratigraphic characterization to characterize the weak zone in the field's condition. So now let's move to the post-breakthrough sealing. So actually the breakthrough is not only part of the story. So once the CO2 is start intruding into the Caprock, the Caprock still can be act as the permeability barrier because it also still have a low permeability. However, once the CO2 is intruding into the Caprock pores, and then now the pores are occupied by both the brine and the CO2, the permeability, the flow mechanism will comply with the multi-phase flow mechanism. So in this here, I would like to emphasize that it's an important like shift in the perspective that the breakthrough pressures tell us when the CO2 is start invading into the Caprock formation, but it does not fully describe what happened after that. So we wanted to understand about the breakthrough mechanism and then sealing integrity of the Caprock as the permeability barrier. We first studying about we simply study about the single phase permeability first. So permeability is calculated by the Darcy's law, and then by injecting water, we evaluate the first single intrinsic permeability. And as you can see, in consistent with the breakthrough pressure, we see that the sand-rich material is has a higher like permeability compared to the clay-rich materials, and sometimes it's a few order of magnitude differences. And then we also found that all the tested material shows an exponential decrease in the permeability with respect to the effective mean stress as the pore structure has been compressed under the high mean stress. And then most of the tested materials are satisfying the typical permeability range for the potential Caprock material. And we plotted this data in terms of the permeability porosity relationship and compare our result with a reference to show some consistency in this plot. At the same time, we also checked the other semi-empirical correlation model based on the clay fraction and found that this model does not fully represent the flow mechanism in the potential Caprock materials. And then now we move to the two-phase flow test. So we use the same core flooding system, but now we need the extra upstream pump because the two-phase means that we need to inject the CO2 and the water simultaneously into the rock specimen. So at the beginning, the specimen is fully saturated with water. After that, we start increasing the fraction of the CO2 with a constant total flow rate to measure until the single CO2 flow injection. And then this result shows the drainage condition of the rocks. So the CO2 is start intruding into the material. But at the same time, we have we can experience the imbibition stage in the field, so that in the testing, the whole series of the testing, we decreasing back the CO2 fraction to the single water injection to measure the hysteresis in the two-phase flow mechanism. And this testing is unique especially for the clay-rich material because most of the testing are performed in the porous rock, mainly because the two-phase flow is mainly strongly correlated with the fluid distribution inside the rock. And then usually this fluid distribution is evaluated by the imaging analysis. However, in the case of the clay-rich material, due to the nanoscale pore structure, we cannot fully measure the fluid distribution because of the resolution limit. So in this study, we developing the idea based on the pore elasticity to measure the effective modulus of the fluid mixture of the rocks. So if we measure the Skempton's B coefficient after each testing, we can recalculating the effective modulus of the fluid mixture. If the CO2 that has been more compressible than the water is more occupying in the rock, we can see the compressibility of the fluids, the pore fluid also change. And based on this observation, we measured the relative permeability curve, which is the relationship between the two-phase flow permeability and then water saturation. And the main finding is that the CO2 still not only for the high breakthrough pressure, the clay-rich materials also exhibit the more favorable properties in terms of the two-phase mechanism. And then the final thing is that this presentation, I only show about the coupled process in terms of the two-phase flow, but we also have some studied about the coupled the hydromechanical chemical responses. Because the CO2 is start dissolving into the in situ brine, and then it generates the acidic fluid. And this acidic fluid react with some carbonate minerals. So this the chemical reaction will change the pore structure and then dominant pore size of the materials. So we use the porosimetry to measure the change of the porosity and then the pore structure. And we developing the constitutive model to predicting how the porosity has been changed over the treatment time. At the same time, we also do some experiments on how this pore fluid chemistry and then the chemical reaction will affect the fluid transport mechanism in the tight materials. So here to conclude, I would like to leave you with the 4 main findings, but the overall the main takeaway is simple. So the heterogeneity in this study, heterogeneity coupled process are controlling the sealing mechanism of the Caprock material, and understanding them is complex but still essential for the safer geological carbon storage. So with that, I would like to acknowledge my collaborator, funding support, and the organization that provide the materials and research support. And we have the couple of papers on the following talk. So if you are interested, you can find the more detail on the experiments and the results. And thank you very much for your attention today. And I would like to happy to take any question.
Thank you very much, Hyunbin. It was a really interesting presentation. In my PhD thesis, I am developing or studying maybe a reservoir rock and how it, let's say, interacts with CO2. We haven't reached yet to the part of studying the Caprock, but I know that it's really hard, so congratulations. Well, so if anyone has any questions, we have a session of questions and answers, so you can just turn on your micro and ask the questions. Are there any questions? Maybe you can try and write them in the chat. If not, well, there's someone saying, thank you, Hyunbin, best slide sets I've ever seen. So, well, I think that maybe we can just go on with the following speaker, and if not, we can try in the following or at the end. If anyone has any reserved questions, we can ask them afterwards. Well, I'll share my screen. Okay, so yes. The next presenter is Edison Martinez Bautista, who is a mining engineer in 2020 and Magister in Mining Engineering 2024 from Universidad Católica del Norte, Antofagasta, Chile. He is currently a PhD candidate in mining at the same university since 2024. Since 2022, he has taught courses and laboratory sessions related to rock mechanics and rock engineering at the undergraduate level in the mining engineering program of the Department of Engineering, of Metallurgical and Mining Engineering, Universidad Católica del Norte. Since 2024, he has also held the position of laboratory technician at the rock mechanics laboratory at the same university. His current doctoral research focuses on the analysis of rock dilatancy and its relationship with the scale effect, aiming to develop a mathematical model capable of describing dilation angle behavior based on laboratory compression tests. Today, he will be presenting a talk entitled Influence of the Scale Effect on the dilatancy and strength behavior of rock masses, an experimental laboratory scale approach. Okay, I will stop sharing my screen, and Edison, I'll leave you the floor.
Thank you for your introduction. We can see.
Yes, we are seeing your screen.
Okay, thank you. Good afternoon, everyone. I'm talking about my presentation. It's about dilatancy and strength behavior of rock masses, but at least on the laboratory scale approach with the study of the scale effects. So let me introduce the content of this presentation. First, I will present the problem and the statement and motivation. Then I will describe the theoretical framework focuses mainly on dilation angle models and a little of scale effect. Next, I will explain the experimental methodology. After that, I will present the results, and finally, we'll conclude and provide the recording of this presentation. Well, we know that underground mining is going deeper, which makes geomechanical conditions more complex. So it's really important to understand the rock mass behavior, especially in the post-peak stage. So, for example, we have one of the deepest mine in the world is Memponen, with a deep of about 4,000 meters. So, well, in Chile, we have a Teniente with about 1,800 meters. So, this mine had a serious problem last year, so we showed that we need to analyze and understand the rock mass behavior. Well, the post-peak behavior can be studied in laboratory conditions using several control tests. The tests allow us to obtain the dilation angle, which quantifies the dilatancy phenomena present on rock mass. This parameter describes plastic deformation, especially around excavation mechatronics. Also, this parameter can be implemented in software like a flat 3D or 2D of Itasca. So the motivation for this study and simple words, first, research on the post-peak is limited because it's a condition we try to avoid in general. However, it's essential to understand the plastic deformation in rock mass. Therefore, we need to increase our knowledge of this behavior. On the other hand, natural discontinuity modify the stress strength response and are part of scale effect. So we must remember that the rock mass is composed of interrock part and discontinuities. Finally, a current dilation model don't include the scale effect, so such a side of discontinuity. So this really important if we want to scale the laboratory scale, results to in situ scale. Well, the stress strain curve is the best way to understand how rock deforms, to understand the mechanical behavior of rock using laboratory samples in laboratory conditions. This curve, we can obtain the main rock properties that describe both pre-peak conditions and post-peak conditions. So for the pre-peak state, we have the biggest strengths on elastic parameters such as Young modulus and Poisson ratio. And damage, we have damage threshold like crack closure, crack initiation, and crack damage. The last one is important because it marks the beginning of plastic behavior on the rock. On the other hand, the post-peak state, mainly we have residual strength and plastic parameters such as plastic shear strength. About the post-peak state, we can say that it describes the transitions from the peak strength to residual strength. Cook and Brown defined 4 types of this behavior: elastic brittle, straight softening, elastic perfectly plastic, and straight hardening. Straight softening is the most relevant to explain to post-peak behavior because it considers the progressive reduction of rock strength. It also includes the dilation angle, which is key to explain dilatancy in the post-peak stage. What is the dilatancy? Basically, it's a volume change experienced by the rock when shear formation occurs within the material, basically producing irreversible or plastic deformation and rock. This parameter, the dilation angle, is calculated from the incremental of actual and volumetric plastic strength. This formulation was proposed by Birmin and DeBoers in 1984. So, we have a problem because it's not always possible to obtain the complete stress strain curve of rock mass. So currently, there are 3 approaches are commonly used to estimate the dilation angle in these cases. Approach 1 is the associative fluid rule, where the dilation angle is equal to the friction angle. And approach 2, it is similar. It's a non-association fluid rule where the dilation angle is taken as constant value, including 0. In this case, Cook and Brown noted that the dilation angle can be related to the friction angle depending on the quality of rock. And approach 3, it's the most relevant as it includes models that relate the dilation angle to confining pressure and plastic shear strain. So nowadays, there are many models, so exactly 11 to represent this approach. And there is no single model or consensus on which one to use. The first model was proposed by Alejandro and Alonso. This model is simpler and includes one additional parameter. It called it plasticity parameter constants. And it's divided into 2 components, one to estimate the peak dilation angle and another to describe the decay of this angle. Well, the second model was proposed by Shao and Kai. This model is purely mathematical and includes 9 parameters without clear physical meaning. So, however, it's difficult to estimate because there is no unique solution. In other words, different combination of 9 parameters can produce the same result. This model is really important because another model based on these models. For Hussein and Shamanish-McCall model, it's similar to the Alejandro and Alonso model, but it's expressed with a different formulation. But it has one part to estimate the peak dilation angle and another part to estimate the decay of this angle. On another part, we have the Walton and Goodrich model. It's more complex because it considers 3 stages to describe the mobilization of dilatancy. We can see in the image. The three parts or three stage are pre-mobilization, mobilization of the peak dilatancy, basically the peak of dilation angle, and after that, post-mobilization dilatancy. One advantage of this model is that this stage can be discrete separately. So it's not necessary to use all parameters at the same time. So another thing about this model, also the peak dilation depends on the rock type. For sedimentary, we can use the Alejandro and Alonso model, and for crystalline rocks like igneous rock, we can use the another equations. The Shen model is similar to Shao and Kai model. It presents the same problem. It doesn't not have a unique solution because it has 12 parameters. After that, we have the Rahu and Everhard model. It's based on the Shao and Kai model combined with the normalization approach of Walton and Diderich. And it used an equation to obtain a simplified form with one parameter. In this case, is the factor n. One model have 7 fitting parameters. Again, we face the same problem. The equation includes too many parameters. The gene model it's another approach that uses a normalization formulation. It's similar to Rakuman-Everhard model. In this case, the internal plastic variable it's between 0 and 1 of value. Finally, we have the most recent models. The Shao and Lee model is a piecewise equation. So its main feature is the concept of the limit dilation angle. This means that at large strains, the dilation angle doesn't go to 0. The Kai model is a variation of the Alejandro and Alonso model. It introduced the parameter K, replacing the fixed value of 0.1 to keep a better mathematical fit. And finally, the one model is based on energy-based approach. The equation depends only the plastic shear strength, but not on confining, but the authors adjust the model separately for each confining levels. Currently, these models, none of these models explicit include side the side and discontinuity in their equations. The scale effect is related to the volume of the rock mass. Smallest scale corresponds to intact rock, while the largest scale represents in the situ conditions. Depending on the volume, the mechanical properties of the rock mass changes. This is important when transferring laboratory results to field scale. But in this case, this effect has not been extensively studied for hospital stage. Between the scale effect, the side effect, and interproc can be identified, where mechanical properties depends on specimen size. This effect has been mainly studied for pitting action strength, can be described using model Cook and Brown or used by Masomi. The main difference between this model appears at small scales, small sample size. The Hooke-Brown model shows only decreasing trend, whereas the user model exhibits an increase in behavior at the small site due to the incorporation of the fractal nature of fractal of discontinuity as proposed by this author. Which model is better, but there is no clear consensus. It may depend on the rock and its structural characteristics. This study considers three types of sample. IBM is the interrock and considers the artificial jointed samples. In this case, JVM 1 plus 2 and JVM plus 2 plus 3. Also, considering 4 sample sites, in this case, 30, 38, 40, 54, and 84 millimeter of diameter of specimen, and with confining levels from 0 to 15 megapascal. In total, we have 299 blanco mera granito were analyzed. The laboratory tests were mainly triaxial and some with some uniaxial tests. The strain measurement were measured using LVDT. The database includes confining pressure, axial displacement, and water volume change inside the triaxials. Additional the measurements, the LVDT measurements were corrected using the methodology proposed by Gonzalez Fernandez et al. Well, for another part, data processing was performed using Python to determine the properties from the stress strain curves, nonlinear fitting, area squared calculus with this programming language. The methodology based on obtaining stress strain curves to evaluate 2 main aspects. The first, the dilation angle, and the proposal of a new model that includes psi. And second, the evaluation of failure criteria considering psi and the presence of this continuity using no models, in this case, more Coulomb, Hooke and Brown, we use a model by Nasomi and include the RS in I residual strength index of by Walton. So it studied Hooke-Brown criterion with ST effect, and a combined criterion were evaluated. Before analyzing the results, it was assumed that elastic behavior remains constant in the post behavior. This means that Jones modulus boson ratios don't change in the post condition itself. This is not the most accurate approach to obtain plastic strength, but it's a lot working without larger database and dataset identify the trends in the dilation angle and the results. The first step in analyzing the proposed model was to evaluate the ratio between friction angle and the average dilation angle along the curve, considering only confining pressure. We can see in the graph it's a decreasing relationship. Based on this, a simple exponential decay model was fitted, including the initial dilation angle or peak dilation angle with a decay factor. So it's similar to proposed by Alejandro Alonso. Based on this, simple exponential decay model was whoever the Earth's square values are low, we can see in this table. So the confining level isn't enough to explain this behavior of the dilation angle. The same equation was then used, but including plastic shear strength. The result improved significantly in this table, so it's a better result. So similarly, psi was added in the exponent of this equation, maintaining the decreased strength. But the results are not fully conclusive, although the fit is acceptable, but the initial dilation angle varies significantly. For example, in the case of the JVM 1+2, the initial angle, the initial dilation angle is equal to 90 degrees. So it doesn't make sense. Based on the previous, it was considered that the diameter may be interdependent on the parameters A and B, so a new equation was proposed. A similar fit was obtained, but with less variation in the dilation angle. In this case, the value of initial angle is similar to the internal friction angle. Here we show experimental results, for example, with a diameter 54 millimeter and for 3 sample types. In general, we have a good fitting between experimental data and the proposed equation can be observed. Additionally, the Hook-Brown criterion was evaluated in the combination with USL model. The first step was to fit the USL model parameters for intact rock, obtaining the corresponding values. And this is one other things it's important. It's to remember that the USL it's a piecewise equation, and the parameter MI is also obtained from Hook-Brown criterion. With this values, the results were evaluated in terms of GCI for each sample types. The values are consistent. Caprock has a GCI of 100 because it doesn't have a damage. JVM 1+2 samples with a GCI of 89, 2+3 with a GCI of 86. So however, the application of this model is not simple. It's required knowledge of these parameters, or maybe can be used another model of Hook-Brown. So it's a little complicated to choose the model. Due to this, an aiming for more practical approach, combinate criterion was proposed. This consists of combining intercrop and discontinuity components component, summing two criteria to describe a single behavior. In this case, we use the Moore-Coulomb criterion, represented for intercrop, and well, what Barton criterion was initially considered for discontinuity. Whoever seen the discontinuity has a smooth undamaged surface. So Moore-Coulomb was also used for the discontinuity. The contribution of each component is controlled by a weighting factor, in this case, factor A. If the factor A is equal to 1, the behavior is dominated by intercrop. If factor A is close to 0, discontinuities dominate. In this case, in this part, friction angle values were determined for the 3 diameters and 3 sample types without decomposition. The total friction angle. An additional reference basic friction angle from Gonzalez et al. For Blanco Mera granite. GCI values also consider intercrop. In this case, GCI is equal to 100, while the other samples have lower values. The Earth Ice Index of Walton was also included to add the residual strength, the analysis, and identify trends for this combined criterion. Well, knowing the total shear strengths of intact and discontinuities, it is possible to estimate factor A. However, in some cases, it cannot be directly solved. So we need a secondary fitting process was applied because it's a non-linear regression. For this, we need using 20 total shear strength data points to the combining criterion was fitting with these points to obtain adjust values of factor A. This results if when comparing GCI and RSI values with factor A, they show similar trends. So this suggests that GCI can be used as a replacement for a factor A, indicating a relationship between these criteria and allowing a mathematical coupling. In this case, for example, internal friction angle depends on GCI, internal friction angle of intercrop, and basic friction angle. And cohesion or total cohesion depends on the GCI and cohesion of the intercrop. Here we show the results for peak strength. In general, the fit is good, with some difference for GBM 2+3 samples at 84 millimeters. For residual strength, all cases show good fit. The conclusions are a 5 parameters model was developed that can include the side effect, unlike existing models. However, the physical meaning of side still needs clarification. The second conclusion, the influence of discontinuity doesn't show a clear trend in the proposed dilation model, although one parameter is close to the friction angle. In this case, the initial dilation angle is similar to the friction angle. Third, it's possible to combine the Hooke-Brown criterion with the usual model, but there are limitations at the interprobe scale, so may present conceptual limitations. Finally, the combining criteria provides a coherent and simplified approach, integrating two main concepts in the rock mass. However, it's necessary to include additional properties such as joint compressive strengths and joint roughness coefficient to generalize this model. This was the reference of my presentation. Thank you for your attention.
Thank you, Edison, for the great presentation. Are there any questions? As I told you before, you can write them on the chat or you can just open your microphone. Okay, I think that today is not the day for making questions. Thank you very much once more, Edison, for participating, and I leave the floor to Kimi.
Thank you.
Thank you, Cecilia. I will turn my screen. So now we have our last presenter. He's Isaac Núñez Morales, who is a geotechnical engineer with experience in slope stabilization, foundation design, and hydrological analysis. And since 2019, he has contributed to major infrastructure and energy projects, including geotechnical monitoring for hydroelectric facilities. Since 2024, he has been part of the Instituto Costarricense de Electricidad, where he has also worked on the characterization of volcanic rocks for renewable energy generation. He holds a master's degree in geotechnical engineering with honors from the University of Costa Rica, supported by applied experience in tunnel reinforcements, dam instrumentation, and advanced geotechnical design. Today, he will be presenting a talk entitled Engineering Behavior of Soft Rock Masses in Costa Rica, Recent Research and Practical Applications. So, Isaac, are you there?
Yeah, thank you. I'm going to start a presentation. Let me see. Okay, let me know if you can see my presentation.
Not yet. Now.
Yeah, I know.
Now it's okay.
Okay. Okay, well, good afternoon or good night maybe, and thank you for your invitation. Today I will present a recent research of the engineering behavior of soft rock masses in Costa Rica, and how different failure mechanisms control the tunnel performance in these materials. The idea of this presentation is to integrate previous research together with a recent numerical modeling application in a Costa Rican tunnel in Pacume, that is an hydraulic tunnel. So to start, we need to define what is a subrock, and this is because we often encounter rock masses with very low compressive strength, sometimes below 10 megapascals. In these cases, traditional rock masses classifications will suggest instability in these tunnels. However, many of these tunnels, in this material, they remain stable. Well, and in other cases, the traditional methods show stability, but they may still lead to a big deformation. So this means that classification alone is not sufficient to explain tunnel behavior. And this creates a paradox that I call here, is why a wheat rock can produce a stable tunnel, or in other part, a wheat rock produce an stable tunnel, but no, it produces with the traditional rock mass classification, it says that it's stable, but it's not. So uh, we need to understanding this and how this occur is the main motivation of this work. So to start, I like to explain what is a soft rock, because according to Kanji in 2014, he says soft rocks are they present several engineering challenges because they are weak, they are deformable, and they are degradable, but they are not soil because they have a rock structure and bonding in a matrix, but they are not a hard rock. They're in the middle. So they are not hard rock because they have a low compressive strength, a high deformability. So when you are in the middle, it's difficult to for example, take samples of this rock. Uh, Also can be difficult to testing. So this lead to conservative designs. And as I said before, when we use traditional rock mass methods like U-system, for example, or rock mass rating, uh, they fail in the characterization of this behavior. So that's why we need to adapt methods to have a deeper understanding of this kind of rock. So in this presentation, we are going to identify the three main behaviors because soft rock masses don't behave in the same way. To start, we are going to start with beam rock behavior. This is where the block matrix interaction dominates the behavior, and continue with massive rock behavior. In this case, is where a microstructure control the properties of their strength, and it doesn't exist a scale effect. And the last one is fracture rock behavior, where the in situ stress can control the response and performance of this kind of rock. Each mechanism require a different engineering interpretation. So we're going to see the first case. This is the case study number 1. This is from beam rock behavior. Was studied by Jimenez 2015. This case, Jimenez studied a conglomerate composed approximately of 50 to 60% of blocks in a fine matrix. The materials was highly heterogeneous, and when he used the traditional methods, these methods were unable to describe this material. So he started to using a numerical modeling to capture this behavior. When he modeled, he used this example. This I'm going to point laser. He made a virtual crop sample and a digitalization of this. Uh, in the third image, he defined a matrix in gray and the block in black and the interface in red. So he found that failure doesn't occur along a single plane. It's occur in a path that is around these blocks. That's why has a key insight of this study. He said that block matrix interaction is that control this behavior. We can see here these are the analysis from FEM. He used he used FEM, and he's shown in this image. We can see the failure path that is controlled by the block distribution. Another important observation in this case is that the sample size doesn't change the mechanical response. We can see here sample base width. When we increase the sample, the uniaxial compressive strength is almost the same, doesn't change. So this means the equivalent strength is a property of the interaction between block and matrix. And this always confirms that BROMs require numerical approaches for a proper characterization. Continue with the second case. In this case, we have massive breccias that was studied from Bindas 2018. In this second case, Bindas study. In this case, Bindas study volcanic breccias with a very low degree of fissuring in a fine-grained matrix. He made multi-scale testing program with uniaxial compression, tensile tests, and volumetric variation. And the results show that there is no significant scale effect. Here is the front of the excavation of the tunnel that remains stable. The samples, different sizes. And an important key insight of this study is that he said that microstructure dominates in star rock properties and control the behavior. So that's why in this tunnel they found a stable performance despite a very low UCS around below 10 megapascals, 10 to 20 megapascals, with high coverage around 100, 500 meters coverage. So one important point of Binda's study was evaluating this scale effect that is present in this graph. We can see here the scale effect in massive volcanic clastic breccias around in here. This is important because typically in fractured rock masses, we expect that the strength decrease when we increase the sample size. So because of the structural defects on the sample. However, in this case, we observe that the strength and deformation modulus remain consistent across different scales. So this indicates that the defect density does not increase significantly with the sample size. Therefore, the behavior is primarily controlled by the material microstructure. This is the justification of this why in this case he justified the use of equivalent continuum to modeling, such a GSI based approach with a GSI around 90 to 100. And in opinion, we can see here that GSI can be seen has an opportunity to use in soft rocks. Meanwhile, in hard rocks can present limitations, the GSI. So so far we have seen two different mechanisms. The first was the beam rock they were controlled by the interaction of block matrix. Second, the massive breccias controlled by the microstructure. But what happens if rock is fractured? Well, in that case, the discontinuities are going to start to influence the stress distribution around the tunnel. So that's why we analyze the case 3. This case is the Pacume tunnel. Just as a brief introduction, Pacume is a project in Costa Rica. It's a multi-purpose water transfer that include an hydraulic tunnel that is going to be excavated through a weak volcanic rock formations that are mainly well tough, like we can see in this geomechanical model. In the green is the well tuff. This tuff is present a very low strength with an uniaxial compression strength around 0.5 to 2.9 megapascals. It also presents a subvertical fracture set of joints, and it has a low coverage, but presents high in situ stress. And when we analyze with Q and rock mass rating, they indicate that the tunnel is stable. In this estimate range is self-support tunnel, but if we use another approaches like the semi-empirical approaches of Aidan, that he indicate that we can analyze a possible squeezing behavior. This is based on this equation that is the strain ratio that is named. With this, we can think that a squeezing approach can be more realistic than traditional classification methods. We can see here that it's a very high squeezing potential to low squeezing, non-squeezing. So, in my opinion, this classification in Q system is mainly in cause for this element, the stress reduction factor from the Q, that cannot fully capture the stress-strain interaction, and therefore may underestimate the deformation potential. So this difference between empirical rock mass classification and semi-empirical squeezing assessment highlights the limitation that can generate this traditional method. So we can continue to use a single approach when evaluating a single a tunnel stability in soft or weak rock masses. In this way, this difference justify using a numerical modeling as a complementary tool to evaluate the mechanical response of this rock during excavation. This is the FEM made with rock science RS2. So to analyze this case, we use two modeling approaches: an explicit model, in this case using fractures directly in the model, and an implicit model using GSI and has a continuum equivalent and Hogan-Brown. Both cases shown that the contrast between blocks and matrix is relatively low. So both modeling approaches show similar trends. Has a third assessment. We use this. We evaluate the tunnel stability using the convergence approach. This is this curve. Same was made with RS rock science, RS2, and so with both results, we see that under the convergence curve, they show favorable conditions where the displacement are small, around 3 to 4 millimeters of displacement. And under the less favorable conditions, we can see that this generates a plastic zones around the tunnel. So this tunnel behavior is governed by the stress-strain interaction and in the rock matrix. So may the tunnel require support. So as a conclusion of this, first we need to say that this studies show that weak rock masses may behave in different ways. Second, that I repeat along the presentation, is that conventional empirical classification systems, such as Q system and rock mass rating, doesn't capture the real mechanical behavior of weak rock masses. So each case is governed by a different dominant failure mechanism. We see the conglomerates, in this case, that are controlled by block matrix interaction. Second case of massive breccias that are controlled by the microstructure. And the third case of fractured tuff that are controlled by stress-strain interaction and discontinuities. So, has a final reflection. We need to say that 50 years ago, empirical classification methods were widely used because advanced numerical tools were not available. But today we can combine empirical models with modern numerical tools and laboratory testing, and we can adapt to each of these mechanisms. So different mechanisms and different engineering approaches, and that's my presentation. This is the reference of this work. So thanks. So.
Thank you, Isaac, for your presentation. Very interesting topic. If anyone has any question, maybe you can turn on your microphone or send it by the chat. Not many questions today.
Hello, can you hear me?
Yes, I think we
Hello?
have one question. Yeah.
Yep. Right. So thank you for Kimi for letting me in. So my name is Alfonso. I'm a geotechnical engineer from Hexagon Mining. So thank you, Isaac, for the massive presentation. So this is very interesting topic. So I want to ask you, Isaac. So in practical ways, we usually use more column criterion to evaluate geotechnical design for soft rock, but in hard rock we usually use generalized Hook-Brown criterion. So when we encounter the rock in the middle of, I will give you an example. If we encounter the rock that have value of UCS approximately around 10 until 15 MPa, and teachers try to apply the validated transition criterion model to establish the more reliable and comprehensive analysis in the medium weak rock. So because if we apply with the more column criterion, it will result misunderestimate. But if we apply with the generalized Brown, it will be more overestimate. What do you think, Isaac?
Yes, well, that is the mainly problem of this kind of rock. There is no right now there is no a methodology to approach of soft rocks is open to Hook and Brown. So we have seen in this case with my partner of worker, we have seen that sorry, I'm looking here, that we need to be creative in these cases because at least in Costa Rica we have this problem with soft rocks, and when we have very low or below 10 to 20 megapascals of interrock, we can see that this is going to happen, and that's why we analyze this part of for example, as I say, using GSI and squeezing potential methods to evaluate. But that's the point. It's difficult to establish this condition when to analyze as a subrock.
Right, so you don't have experience with applying validate transition criterion model.
With what? Sorry?
So you don't have experience in applying validated transition model criterion.
No,
right.
I only apply in this tunnel. Yeah, this case. Yes.
All right. Thanks so much for your questions, Isaac.
Okay.
Sorry for your
Thanks.
answer. Thank you.
Any other question? Maybe we have time for another one. So thank you, Isaac. Very interesting topic. Many research can be done in this area, so it's very interesting that you can share your experience in Costa Rica. So thank you very much for the presentation. And I will share just to finish. And now we are at the end of this 19th ISRM Young Members Seminar. So on behalf of the organizing committee, I would like to thank to the ISRM for helping us in the organization of this event. And I also would like to thank to Dr. Lucas Bellini Machado, Dr. Hyunbin Kim, Mr. Edison Martinez Bautista, and Mr. Isaac Núñez Morales for their very interesting and valuable presentation that address very relevant topics in rock mechanics and rock engineering. Yeah, we hope that this seminar provides you with new insights and new challenges for future research. And further information for next events will be available on the ISRM newsletter and website. So keep in touch to not lose the next webinar and seminar. And thank you very much for your participation, and have a wonderful and safe day or night, depending on where you are.